Hi, I'm excited to share our work titled Compact 3D Gaussian Representation for Radiance Field. 3D Gaussian Splotting, 3DGS, has recently emerged as an alternative 3D representation that leverages a point-based representation associated with 3D Gaussian attributes and adopts the rasterization pipeline to render the images rather than volumetric rendering. It achieves high rendering quality, fast training, and real-time rendering. However, a significant drawback arises as 3DGS entails a substantial number of 3D Gaussians to maintain the high fidelity of the rendered images. Furthermore, each Gaussian is characterized by 59 parameters, such as position, covariance, and view-dependent color, which require a large amount of memory and storage. In this work, we place a specific emphasis on two key objectives: reducing the number of Gaussian points and compressing the Gaussian attributes. To reduce the number of Gaussians, we mask out non-essential Gaussians by learning each Gaussian's actual impact on rendering quality. This allows the reduced redundancy of Gaussians, while preserving high-quality rendering. In the original 3DGS, each Gaussian has its own attributes, and it does not exploit spatial redundancy, which has been widely utilized for various types of signal compression. For example, neighboring Gaussians may share similar color attributes, and we can reuse similar colors from neighboring Gaussians. Given this motivation, we incorporate a grid-based neural field to efficiently represent view-dependent colors, rather than using per-Gaussian color attributes. In contrast to the color attribute, the majority of Gaussians exhibit similar geometry, with limited variation in scale and rotation attributes. Therefore, we introduce a codebook-based approach for modeling the geometry of Gaussians. Let's talk about more details of our proposal. We introduce an additional mask parameter and generate binary masks by applying a threshold to it. As it is not feasible to calculate gradients from binarized masks, we employ the straight-through estimator. We apply these binary masks not only on the opacities, but also on the non-negative scale attributes that determine the volume geometry of Gaussians. Small-sized Gaussians, due to their minimal volume, have a negligible contribution to the overall rendering quality, often to the point where their effect is essentially imperceptible. In such cases, it becomes highly beneficial to identify and remove such unessential Gaussians. We can balance the accurate rendering and the number of Gaussians during training by adding masking loss in conjunction with rendering loss. Once training is completed, we remove the masked Gaussians, so the mask parameter or binary mask does not need to be stored. A number of Gaussians collectively construct a single scene, where similar geometric components can be shared throughout the entire volume. Therefore, we propose a codebook learned for representative geometric attributes, including scale and rotation, by employing vector quantization. As naively applying vector quantization requires high computational complexity and large GPU memory, we adopt residual vector quantization that cascades multiple stages of vector quantization. To ensure fast and optimal training, we apply it only for the last 1K training iterations. Each Gaussian in 3DGS requires 48 of the total 59 parameters to represent spherical harmonics, to model the different colors according to the viewing direction. Instead of using this naive approach, we propose representing the view-dependent color of each Gaussian by exploiting a grid-based neural field, instant-NGP. Specifically, we can track the unbounded position of each Gaussian to the bounded range, and input them into hash grids. And then the resulting feature and the view direction are fed into the MLP to represent view-dependent color. Now, we have a reduced number of Gaussians with compact attributes, which are used to render images. The entire model is trained end-to-end based on the rendering loss. Our approach consistently reduces the storage requirements significantly and enhances the rendering speed, while performing accurate reconstruction, comparable to 3DGS. With post-processing such as quantization, pruning and Huffman coding, our model is further downsized by over 40% regardless of dataset. Consequently, we achieve more than 25 times compression from 3DGS, while maintaining high performance. The qualitative results also demonstrates the high-quality reconstruction with significantly reduced storage. Although the number of Gaussians is noticeably reduced, as demonstrated by the sparser points in visualization, the rendered result retains high quality without visible difference. The majority of Gaussians maintain identical geometry regardless of the application of AlVQ, with only a few exhibiting very subtle geometric distortions that are hardly noticeable. We also explore the patterns of learned indices across each stage of AlVQ. The initial stage exhibits an even distribution, with a large magnitude of codes. As the stages progress, the magnitude of codes decreases, indicating that the residuals of each stage have been effectively trained to represent geometry. More detailed ablation studies, including quantitative results, can be found in the paper. In summary, our method consistently showed about 15 times reduced storage and enhanced rendering speed in end-to-end training, while maintaining scene representation quality. Our method can benefit from simple post-processing techniques, consequently achieving over 25 times compression throughout the datasets. Our approach set a new benchmark with high visual quality, compactness, fast training, and real-time rendering, standing as a comprehensive solution for efficient 3D representation. For additional information, please check our project page. Thank you.